don't acknowledge that weather is an issue, but that's my own hang-ups and foibles or whatever. But like I said, this week, dealing with some other issues that I was kind of glad to have a little bit of extra time, but that meant that I gave out some pretty poor videos. Yours were better than some, though, on Thursday or Wednesday. When I made those that morning, I got up at like 4:30 because we didn't know we were going to be remote until like 8 o'clock the night before. I mean, we knew, but we didn't know. We didn't get the official word. And so, yeah, that's a communication problem with our campus. But nonetheless, I did what I could. Um, so let's talk about the various things that you had on your homeworks. So basically, the two homeworks, and I don't want to collect them. I think I emailed you. I forgot to. I was so excited about it. Forgot to bring my self-inking stamp, check mark, thumbs up stamp. So don't worry. I'll bring it on Monday. The problem is that I have two backpacks. I have my professional backpack, as you can see. It's more professional. And then I have my biking backpack that gets all mucky. So it's the stamp is still in the biking backpack. I'll transfer it to this when I get back to my office after class so that on Monday I'll have it. Don't worry. We'll deal with that on Monday. It's just that I can't deal with all these papers, especially with, and also I don't want people to be printing their stuff and using up their printing budget. So, and I appreciate the dedication to the class though. Okay, so getting back, yeah, so Tuesday's lesson was about work. So that I suspect most of you, especially those of you who've had physics, didn't have much trouble with the gorilla or anyone else or anything else where you're dealing with work is force times distance, right? It's simple as that. And if you're dealing with some sort of a static force with a static distance, done. It's easy. It's when things turn into variables like number 3 that things when it had trouble. So let's deal with that first assignment, the one that was assigned on Tuesday, due on, oh wait, we have to back up further, don't we? There was stuff, wait, did anyone have any issues with the stuff that was due on Tuesday? Did I go over that stuff?
You had a video.
I had a video, okay. Watch the video, I guess. Okay, so let's deal with, okay, so we'll deal with this first. The first part, so these are variable forces. Let me just review what the things were. You had the gorilla, that was a static force. You had lifting a rock, that's, anytime you have something that is that something's not changing, like I didn't bring my book. That would be an excellent example because the book is like 2 kilograms. But you have some object, you lift it, you're overcoming the force of gravity, and it doesn't matter how fast you lift it, fast or slow, it's just force times distance is work. You have to make sure you're in force though. That is to say that force in imperial units is pounds, force in metric is newtons. Yes, Hayden, you had a question? Yes. We're going to pretend that it doesn't happen. We're going to, well, and for all intents and purposes, you can go up to the top of the building here, technically slightly less gravity, but in reality, it's so small of a difference that it's immeasurable with the tools that we would have access to. So 9.8 meters per second squared here and upstairs. Don't worry about that. Yeah, so yeah, if we were talking about shooting a rocket to Mars, escaping, doing escape, that would be, that would be a variable force because as the rocket got further and further away from the Earth, you would have less and less force to overcome. So the work done there, you're right. But yes, there would be a lot of variables, lots of variables that you'd have to, but here we're trying to keep it simple. You can dream though, you dare to dream. Okay, so was there any difficulty with these? The first one with variable force is number 3. And then didn't we have some ropes that we had to do? I forget where they are. Yeah, there's some ropes. I think that was part of that assignment. So is there any trouble with the ropes or with the variable force? Yeah, the quiz that I have prepared, if we get to it, no fears. If we get to it, the quiz is just a rope. It's a rope. It's simple. So hopefully you won't have trouble with that. Yeah, there will be also a test. I've got the practice test online. So I haven't sent the test to the printer yet, though. I did with my stats test because I know what's going to happen. But I don't know about this class. We'll do our best. Okay, so we're good with that. The second thing, so on Wednesday, the videos were about Hooke's law, springs. So springs, Hooke's law, and the variable force there. Oh, I should have brought some springs with me. I guess I have a sort of a spring here. This thing is elastic, so elastics, this is a spring. That is to say that the amount of force that is pulling my hands together is greater the further apart that I pull these two ends of this elastic band. So anything like this would probably follow Hooke's law, and that the force is proportional to how far from rest you've pulled this. So here's the resting position, and then if I pull it 1 inch, and then the amount of force required is going to be exactly half of pulling it 2 inches. So every time you add another inch, you add more force. So that's the idea there with springs. We had some springs on the homework. They're up here somewhere. But did you have trouble with any of the springs? I think I suspect where all the problems occurred, but I'm happy. Let's deal with the springs first. Get the springs out of the way. Bounce, bounce. Okay, yeah, you're just like, let's get to those swimming pools. We want to know how much work. Yeah, what do you think, Fred? Let's take a look at 10. Thank you. I don't even know where, I don't see a 5. You're talking about number 10? This one? This one right here?
Oh, no, it's 19.
19. Okay, 19. See, 19. Oh, the chain. Okay, yeah. Oh, and it's like 2 separate. Did I copy that? Just a minute. Let me just see. Did I copy it? I don't know. I might have copied it somewhere. 19. Oh, there it is. Oh, yeah, we did it. Oh, okay. Oh, yeah, 19 was tricky, wasn't it? So here's the deal with 19 is that you've got your rope or whatever it is. This scarf can be a good stand-in for whatever it is that we're picking up, or chain or whatever it is. So it's hanging down, and we're going to grab the bottom of it and lift the bottom up to where the top is. So as you do this, you could think of it in a bunch of different ways, but the way that, I don't know, let me just make sure I do it the same way that I did here. Yeah, okay. So the way that I'm thinking of it is on this scarf, you could imagine that the scarf is made up of a bunch of little slices. And so you can imagine one little slice, and if you look at the scarf, there are like the knitting. I'm sure this is machine knitted, but the knitting has little stripes, little like bands of threading, and the yarn. And so anyway, each of those bands is going to have to travel a different distance. So that was my delta x. Delta x is the thickness of the piece. So I've got a piece that's a little delta x piece. And so I want to know how much work is done in moving that little piece up to wherever it ends up here. And so you have to think through, like, how far is that going to move? So let's just pick a piece that we can all see easily. So the R, the bottom of the R in soccer. So where does that R end up? So as I lift this up, that R ends up the same distance from the top as it was from the bottom. So if I call X the distance from the bottom for this little delta X piece, then the amount of travel is the length of the scarf minus 2 times that X, because now we're X units from the top. Down here, we were X units from the bottom. So in terms of this actual rope, the whole rope is 10 units long. And so this is that little piece, that delta X piece. It's going to travel from here up to here, which is going to be 10 minus 2 times X, whatever X is. So that's where that piece came in. Oh, and we're thinking through that work. Whoa, that's funky. Let me do this. Work, just a minute, change colors a little bit. Okay, work is force times distance. Always go back to first principles with these problems. It's going to be way easier. Just checking, want to make sure I'm recording. So if we go back to the beginning, the basic formulas, you can say, okay, that little tiny chunk, we're going to, the distance traveled, so the distance for that chunk is 10 minus 2x. And I realize we're going to get to your question, Fred, in just a minute. But let me see if I can get the rest of this done. The force is how much does this, is it a chain? Yeah, it's a chain. So how much does the chain weigh? 25 pounds. So we have 25 pounds. But that 25 pounds is distributed over 10 feet. So the density of the thing, if you want to think of it as density, is 2.5 pounds per foot. So we'll take that 2.5 pounds per foot and multiply it by delta x. So like if I have 1/10 of a foot, then the little piece that I'm talking about would weigh 0.25 pounds. If it's 1/100th of a foot, if that's what delta x is, then it would be 0.025 pounds. So whatever it is, that's how much it weighs. And in English units or imperial units, weight, pounds is force. So pounds measures the amount of force that we place on the ground, if you will. And so the force here is going to be 2.5 delta x. So 2.5 times however big this little sliver is. And then we can just do force times distance. So now this is easy. Force times distance is 10 minus 2x times 2.5 delta x. Okay, so I'm guessing that's not where the question, because you were mentioning the 5, right? You wanted to know where the... Okay, so now that answers the question about the 10 minus 2x, or is it still not clear? Okay, well, let me just wrap this up and then we can move forward. But the last bit, of course, is to recognize that we're only going to be lifting the portion of the scarf up to halfway up. So as I lift this end up, the top half of the scarf doesn't move. It's just the bottom half that moves. And so the closer you are to the center, the less you move. But so I just have to integrate from x equals 0, that's the very bottom of the scarf or the chain, to whatever the middle is. So 0 to 5 for this particular chain. Oh yeah, sorry video people, you're not going to be able to see the scarf. But you can imagine that I've got a scarf with cougars. Go Cougars! So the R on the scarf is the last letter. Soccer, MVNU soccer, that's what it says. Okay, yeah, so anyway, we're going to integrate this whole thing from 0 to 5. That'll be from here to here. That's where what gets moved with this chain. And it's going to be 2.5 times 10 minus 2x dx. And that's easy. Nice, easy, linear polynomial. Hopefully that's what I did. Is that what I did? Yeah, it looks like it. Yeah. And did I give up? No, I actually did it. 125 halves, 62.5. Very nice. So, and that's in foot pounds because it's feet times pounds, pounds times feet. All right, so is that helps you out there, Red? Anyone else have problems with this one? Just want to make sure. Any of the issues with picking up ropes, picking up things, doing springs. We'll get to the tanks in a minute. What do you think, Eli?
I'm just interested that I definitely did it wrong, but
Interesting. Well, okay, so let me just comment on that. If you do it wrong and get the right answer, it might be that you're doing right, but using a different perspective than I am. Because there's different ways to view the situation here. So the way that I've set this up, I'm thinking in terms of picking up a little sliver of this particular chain. If instead you think of picking up the whole, like whatever portion of the chain you're picking it up by a certain distance, if the delta x is the distance, not like here, let me just show you up here. The delta x is part of the force. There is a way to turn this around so that instead of delta x being part of the force, the delta x is part of the distance. So for example, here at this point, I'm going to just take a photograph of, or pause the lifting of the scarf or the chain, and then I'm going to move it up by another delta x, delta x, delta x. So if you do that, your setup would look different. This might even look a little different, but you'd get the same answer. So it just depends on your perspective. So I'm not convinced that you did it wrong and got the right answer. You might have done it right and got the right answer. We could talk later though, if you're really curious, and I'd be curious to see what you had. Yeah, it's irritating though, right? Math, you can do lots of different ways and get the same answer. It's also beautiful. All right, anything else about this one or anything other than the tanks? We're going to do the tanks soon. What do you think, Hayden? We can. Backing it up. Backing it up. I know, I thought we were done with 7, but we're going to do 7 now. Okay. Okay, a force of 10 pounds. Let me just walk through the setup of this thing, and then we will, I'll leave the calculus. The calculus is easy once you have it set up. So a force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. Now, we've got a problem right off the bat with units. Most of the time when we're talking about problems with pounds, we're going to use feet as the distance unit. So especially when you think of work done, it's usually foot pounds. Same thing with like if you have a torque wrench, usually it's foot pounds is the amount of torque. Similar units to work. So I'm going to convert all of this to pounds, or no, feet. So that means that 4 inches is 1/3 of a foot. 6 inches is 1/2 of a foot. So once you have that, you probably will get it right. So if you didn't do that, then you're going to get an answer that is probably going, let's see, foot pounds. It'll be 12 times, I think, the answer in the back of the book, because you're using inch pounds instead of foot pounds. But yeah, let's just whip through this. I'll get it set up. 10 pounds for 1/3 of a foot. And that means that, okay, 12.5. Okay, just wanted to get everything, all the numbers memorized. Okay, so we have, this is number 7, 10 pounds. We'll stretch this thing 1/3 of a foot. And we want to know work from 0 to 1/2. Do I have all the information we need? Sure. Okay, so first thing, Hooke's law, spring constant. Force is equal to the constant times the distance that you've stretched the spring. And so here we have 10 pounds is going to be K times 1/3 of a foot. So K is 30. If you did this with 4, you would have K is equal to 10/4 or 2.5. Different number, same answer in the end, just different units. Okay, the work done. Okay, that's easy enough. We do the integral from 0 to 1/2 of, so think about incremental. So this is the idea. I know I'm not, well, I don't know if I ever did this. So let me do it now. Is that we're incrementally stretching the spring. So if you have this spring at some point and we want to stretch it an additional delta x. So that's the idea here. So x is the distance away from the spring being at rest. So we've already stretched the spring x units. I'm going to stretch it an additional delta x unit. So work is equal to force times distance. And so the force in this case is K times X, that Hooke's law. So the force will be 30x. The distance is delta x, because that's the only, we're gonna do that work for a little tiny increment, and then we're gonna have to recalibrate, if you will, and do a little bit more work. So we're doing little tiny incremental works. So the work will be 30x delta x. So this will be the integral of 30x dx. If you do this, you'll get the back of the book answer. If you did it using inches instead of feet, then you probably got 12 times the back of the book answer, or 1/12. I forget which way it went, but it's going to be off by a factor of 12. Whew. All right. Anything else about 7 before I move on? We're going to get to the pipes and the water. It's the best part, I know. All right. We're going to do this. Okay. So let's do pipes. Where are we? So we had, where are the other 2? Weren't there 4? Okay, yeah, these two, and there are two more. I'm sure they're somewhere. I'll find them. I think they're on a different, I had them on a different place, but let's deal with number 23 here, and I'll go dig out number, was it 25? So you had to do 23 and 25? Yes, Hayden? Oh, I think, yeah, okay, I'll find it. Not to worry. Yeah, sorry, he's referring to, I may have deleted it, actually. So, but it's okay, because I can always re-download it, it's fine, these images. But anyway, let's deal with this one first. Just to remind you what we did, or what I did, I had something similar to this. I think it was, what is it, number 26? Had like a wedge shape that you were emptying this swimming pool or whatever it was. So this is a little different than that. So let's go ahead. We're going to do this relatively quickly, but here's the idea, is that we're going to break up this work that was going to be done in pumping this tank empty. We're going to think about it in terms of each of the little tiny pieces of water. So each of these rectangular, so here is one rectangular piece of water. I know it's kind of hard to see. I'm going to redraw it in just a minute. But imagine that little chunk. I want to know how much work is done for that little chunk, and that little chunk is going to be delta x units tall. And what is my x? My x, and I know you might have put your x elsewhere, my x is going to be how far from the bottom of the tank I am, right? So if you used x up here, that's fine, but your diagram will look a little different. So kind of like with Eli and me with that other problem, you might have done it using a different perspective. Like if your x is up here somewhere, but it's still right. It just, the work would look different. Okay, so let me take this one chunk. This is going to be the easiest way to do this, by the way. So here it is. This is this rectangular solid, if you will. So think of it. I know it's not exactly a rectangle, but we're approximating it with a rectangle. This thing is delta x units thick. We know from the diagram that this thing is 8 meters long. And then the last bit of information is how wide this thing is. Well, to figure out how wide it is, notice that this triangle, the end of the tank, let me draw that end of the tank here. The end of the tank is a triangle that has this interesting property, and that is that the height of the rectangle is the same as its width. So here, just to show you, there it is. So I'm just taking this end of this triangle here, redrawing it there, just to show you where it is. So what that means is that if I chop this triangle off right there, the height of this smaller triangle will also be equal to the width of the top here, because this would be a similar triangle. I'm actually going to superimpose this on this diagram here. See this here? This distance is x, and so is this distance. So whatever distance I have from the vertex down here is the same as the distance across the top. If this is x, then this will be x. And so the final volume of this particular slice of water is going to be 8x delta x. Just multiply the dimensions together because it's a rectangular box. That's the volume, and we're dealing with metric units. So because it's metric, it's easier. So in metric, here are the two things you need to know. These will usually be given. Were they given anywhere? Oh yeah, well, here's the imperial units. They don't have metric, but metric is so easy that we all know that water has a density is equal to 1,000 kilograms per cubic meter. Now, if you didn't know that, you might know that water has a density, well, distilled water, has a density of 1 gram per cubic centimeter. And then you could just do some unit conversions to get this, That's another option. I think I might have done something like that on the video. I was like, oh, 100 centimeters and blah, 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 blah. Yeah. So anyway, so that's the density of water. The other little nugget that you'll need is the acceleration due to gravity, but we all know that is 9.8 or so meters per second. I think actually even right here, it would probably be more like 9.81, 9.805, something like that. So this is an approximation that we use because we don't want to have to make things more complicated. So this is, yeah, sorry, this should be like this. This is 9.8 meters per second squared. I think that's right. Whatever, doesn't matter. Well, yeah, it does. Okay, so we have the volume. Then we can have the mass. The mass of this water will be 1,000 times the volume, because the volume is cubic meters. So take the volume, multiply it by 1,000, because density of water is 1,000 kilograms per cubic meter. Then we need the force. The force is mass times acceleration, which I realize that if you are, physics nerd, you're doing great. The people who are like the math majors, I know you're suffering, but try your best. You might remember this from your high school physics, or if you took physics here, maybe. But anyway, so force is mass times acceleration. I've just put that together. And so I'll just write it like this. Now, honestly, once you have that, the rest of this is almost comically easy, because that's the hard part. We've done all the hard stuff. Let's do the easy stuff. But let me make sure that everyone's comfortable with the hard stuff, because this is the hard stuff. Yeah, it's going to be easier in just a minute. So is there any complaints or people saying, what? That may be all you can think. Or maybe there's a particular, like the 8. Does the 8 make sense? The 8's there, isn't it? Yeah, I'm always worried that I'm going to copy incorrectly. Okay, we're okay with this? Okay, yeah. So let's put it together. Like I said, now we're just going to just finish it up. The work. So work is force times distance. We have the force. Let's figure out the distance. I guess this is not trivial. It's a little bit more than trivial, but let's see, how far are we going to move this thing, this water? So looking at this picture, this particular piece of water is going to have to move from where it is up to right here. I need to know this distance from there to there. Well, that's easy enough, because the total distance from the bottom of this particular tank up to the top of the pipe is 5 meters. And so this here, the purple part, will be 5 minus x. So in other words, if x is 3, this top layer of water just has to go up the pipe. The bottom, the very bottom of the tank, that has to travel all the way up to the top of the pipe. So it's got a lot further to go. And I'm guessing that you would actually have this, like the pipe would extend to the bottom, of course, so that you'd be pumping the entire tank. But there it is. Okay, so the distance is 5 minus x. So the work done will be, the integral of 5 minus x times 9,800 times 8x dx. Last thing is, what are our limits? Well, look at this. X is going to start down here where x equals 0, and it's going to end up here. That's going to be the last of the slices, or the first, depending on your perspective, is going to be when x equals 3. So we're going to be adding up all of the work done for all of the slices between 0 and 3, or between 3 and 0, whatever your perspective is. And so then the rest of it is just basic calculus. I mean, simple, nice polynomial. You have an easy, it's just a quadratic here. So you don't even have to do FOIL. So that one, I don't think we need to do anymore. But the setup is the hard part, and I acknowledge that. That is hard. It's hard. I mean, look at all of this. Look at all that. That was just to get the setup. So I guess also, let me just mention this and then we'll take questions. Sometimes when students look at problems like this, they look at this and they erroneously think that they should be able to go directly from this to the purple down there. No, there is a lot that's going to go into getting that purple. You have to think through the diagram, the mass, and all this stuff. So be patient with these problems. They're hard. That's why I only assigned 2 of them, is because I know they're hard. So other questions, concerns, or worries? Yeah, what do you think, Hayden?
So why do you go to the 3 for primary versus going all the way up to 5?
Okay, so here's the deal. I don't know how thick that tube is. I'm assuming it's a capillary tube, all right? So in other words, if that tube is so small that the water inside the tube is negligible, then all I'm really measuring is how much work is done in moving this water up to the top of that tube. So I'm assuming that that tube is either empty at the beginning, so the only thing that's full is the tank. And if this tube is empty, then we don't care about it because there's no water to be worked on. Or it's so skinny, like as skinny as this pencil, that it's negligible. The amount of error is going to be none. So if you really want to worry about that tube, you're going to need to know the dimensions of the tube. Yeah, I think the implication of the description at the stem of the problem is that you have the tank filled with water, and then you're going to pump the water that's in the tank. The tube is not part of the tank, up and out. So, anything else? Other concerns with the way this is set up? All right, let's do the next one. Let me go find the next one. Hold on a sec. Is this it? Oh yeah, this is what I was deleting stuff from. I hope it's not. Oh, well, there it is. It's this one, right? Okay, let me I'll just take a photo of, or a screenshot, just a minute. So then we can deal with this. The frustum, sorry, I always get that wrong. Frustum of a right circular cone. Let's put this back here so it's all together in one big happy family. Okay, so there it is. Whew. Same thing though, we're going to do exactly the same thing. If you understood what we did with that triangular thing, this is no different. It's just a circular tank instead of triangular. It's going to be the same, trust me. Let's go ahead and do it. I know you don't trust me. Let's do it. Okay, so so the first thing that we did was we drew a slice. In this case, my slice is going to be like a disc of sorts. All right, Americo, are you okay? I'm not complaining. I just want to make sure that we're not going ahead of you guys. Yeah. Oh, do you want, on the last one, do we need to, I don't mind you discussing it. I just don't want to go ahead until you're happy. So if there is something that you're not happy with, go ahead. I'm not trying to call you out or anything. So take a minute and figure it out. Oh, where? Down here? Yeah. Actually, you want to know the next step? Is that it? Yeah, next step. Probably, I don't know what I did on the video or anywhere if I did this. Here's what I would do at this stage. But are you happy with the purple? Yeah. Wait, Burke. Andrew. I'm trying to remember your name. Sorry, it's been a week. But anyway, so at this stage, so as long as you're happy with the purple, the next step, I say, oh yeah, you can do it yourself. But let me just show you the next step, and then you'll say, oh yeah, the rest of it is super easy. So the next step that I would do is I would take that 9,800 because it's such a big number. I'll just stick it out front, and then I'll just move this stuff. So this will be 40x minus 8x squared, just to make things easy, because I can deal with the smaller numbers much easier, like 40x That's 20x squared when you do the antiderivative. And the 8x squared is going to become 8/3 x cubed. Then I'll plug in my limits, and then I'll use my calculator at the end to deal with the 9800. But yeah, you can do it however you feel comfortable, though. If you want, you can multiply 9800 times 40 ahead of time and then do the antiderivative. But it's whatever you're most comfortable with. Yeah, so when I get to like a stage like this and I say, oh, it's just easy from here, I don't know, if there's some nuts and bolts issues that you guys need, I don't mind telling you. I just figure that this is the hard part, getting the setup. It's hard. Let's name it for what it is. Yeah, so are you happy enough? Yeah, I just don't want to go ahead if you're still lingering, that's all. If anyone else wants to linger more on this one, we can linger. I came in today thinking, I have no idea what we're going to do because I didn't know how far you guys got. So this is good. We're getting this done. Hayden? There's at least one on the practice test. So you'll have at least one on the practice test that you can do. So we'll talk about that one next week, but it's already on Moodle. So the practice test, I think I uploaded it yesterday. So if you go to tests on Moodle, you should be able to see it. And yeah, we could make more if you want, but see how you do with the one. All right, let's go on to this frustum. Where are we? Where is it? There it is. Beautiful. It's so big. Okay, so as with the last problem, think of, imagine slicing this. We're going to get a slice of this water. And that slice of the water is going to look like this. And this thing has some sort of a radius. We know the thickness is going to be delta x. So I guess we're going to have to settle on what we mean by x. I think I would like to make x the distance from the top. Yeah, I don't know. There's no good way. Let's do distance from the bottom. So how far from the bottom? It really doesn't matter. In the end, it's not going to matter. It's just going to matter with, I'm trying to avoid as much complication as possible. So I think we'll just do that. Okay, so in order to figure out the radius of this disk, we're going to have to rely on some geometry. So bear with me for a minute. I'm going to take that piece of that cone, and I'm going to draw it like a trapezoid. So imagine looking at it completely side on. So we're just looking at it. So tilt this upward so that we can't see the top or the bottom. We're just looking at the side. It would look something like this. Let me put these measurements in here. So this measurement is 6. This measurement is 3. This measurement is 8. And let's just do this really quick. I know that's a lot of numbers there, but I've just broken this this picture up into some logical, at least I think it's logical, ways of doing this, because then this gives me a nice right triangle, and this thing is a rectangle. And so now let's imagine where this slice is going to appear. It's going to appear right here, sort of in the middle, x units up from the bottom. That means this distance is, it's hopefully level. So this distance is x. And what I want to know is, I would like to know this distance here. So this is a little bit of challenging geometry, but some of you probably rose to the task already. Let's go ahead and do it though. So as I look at this, we're going to have two pieces. We have this 3. That's this. You know what? I'm going to have to erase something because there's too much here. There. Okay, so we have this distance, which is 3. And then we have this distance, which we're going to have to think about. Now, the way that we're going to think about it is we're going to realize that this triangle, this little triangle, is similar to this big triangle. So even if you never had trigonometry, you probably realize that similar triangles have proportions the same. For example, this side is 3/8 of this side. So you have 8 and 3. So the proportions are 3 to 8, 8 to 3. So whatever this is, this thing, this little piece, will be 3/8 of this. So that's what I'm going to put here, is that the little piece here is 3/8 of whatever x is. So that means that on my picture over here, the radius is 3 plus 3/8 of x. I think that is probably the worst part of this problem, other than the algebra that we're going to have to cope with. Because the algebra for this one is kind of ugly. But that understanding that the radius of this distance here is 3 plus 3/8 x. So take a minute, let that sink in, meditate on that picture for a minute, and then we'll get the rest. What do you think, Michael?
So could you, instead of, I'm not sure if this will work or not, but couldn't you just start with the triangle instead of starting with the trapezoid? Because that's what I did. I have no idea if I got it right, but
So you just worried about this little triangle here.
yeah, I like hit a triangle rather than
I mean, that's the thing that is the problem, isn't it? Is the triangle. So you're saying you have this triangle here, this is an 8, this is a 3. Is that what you have?
I made it 8 and 6.
Ah, but it's not 6. Yeah, that's the issue. Now, I suppose you might be able to do this, continue this cone downward, in which case you could say, okay, if you have a 6 here, this is going to be 16. For this cone to continue all the way down to a point. But we've got it sliced off. Yeah, I think we need the trapezoid for that reason. To bear in mind that it's not 6 across the top of the triangle. It's 3, and it's because this is a trapezoid, not a triangle. So let's see if I get rid of all of these measurements. Get rid of this. So every dot is going away one at a time. There. Anything else? Other complaints? What do you think, Hayden? The 3/8? Okay.
I understand the 3 up top, and that is half of the full diameter, which just take the half of the smaller diameter then at that point.
Well, the 3. So I'm gonna kind of do what Michael was suggesting, and I'm gonna just take that triangle, the right triangle there, and you say you believe this, and you believe this.
I understand.
Okay, let's go just work with those two numbers. Well, this 3 up here, you're less certain about?
Well, I understand that, if you never always splits that perfectly, but I understand that
Yeah, because this is, yeah, down here you have 3, so the up here would have to be 3. As long as these are parallel, and the top is 6, so that's split there into 3. Like if the bottom was 2, then you'd have 2 and 4 at the top, but it's 3 and 3. Okay, so now let's figure out where the 3/8 came from. So there's 3 on the top, 8 on the bottom. So similar triangles, what that just means is that if you have another triangle, okay, this is not going to be to scale, but if this triangle had a 6 up here, then this side would have to be 16 for it to be proportional, wouldn't it? Because we're doubling the sides. If, on the other hand, we split the sides in half and had 1.5 over up there, then the side of the triangle would be 4, because that would be half. These are just properties of similar triangles that you learned in geometry class. So I need a formula, though, that will tell me what happens if, okay, maybe I should have gone with, let's just do one more. let's say that I have one where 2 is on that side. Well, 2 is 1/4 of 8. So on the top, I will have 1/4 of 3, which is 3/4. So that's the idea with the similar triangles. Now for the hard one is what happens when you have x over here? How big is this side? And so if you compare all of these, especially this one, but every other one, you'll notice that the top is related to the side in the sense that the top is 3/8 of this side. So multiply 2 times 3/8, you get 4. Multiply 8 times 3/8, you'll get 3. 16 times 3/8 is 6. 4 times 3/8 is 1.5. So each time this top is 3/8 of whatever's over here, and that's where the 3/8 came from. We could use the tangent to get the 3/8, but I suspect that most of you would prefer me not to write tangent. Okay, I won't. So yeah, the angle, by the way, would be this angle. Yeah, once I throw an angle in there, I think that would cause more grief than it's worth. Okay, it's almost 10, so we have about 10 minutes left. We're going to finish this one. But I want to make sure everyone's comfortable. I mean, like I said, I didn't know where you guys would be in this material. We haven't seen each other all week, so it's good to be together again. And I don't mind taking today to sort of pick up the pieces. On Monday, we will do averages. It's easy. Average is easy compared to this. Trust me, super easy. Any other issues before we go on to getting the answer here? Because we're there. We're doing it. We're doing great. You guys okay back there? You're getting along. Okay, good. Yeah, no, it's good. This is great. I mean, it's good to have people that if you don't have someone you're working with, this is good. Because outside of class, how are you going to study for the test next week? You're going to get together with your buddies, and you're all going to get A's, right? Good. So, okay, let's go ahead and finish this up now. So we're doing the same process we did with this last one. Where is the last one? Just to review, there it is. So just to remind you, I had this piece. I figured out the volume, figured out the mass, and then the force. We're going to do the same thing with these pieces for this circular thing. So it's the same exact thing. So let's go down here, do the same process. I have the picture. Let's get the volume. This is going to be painful, though. The volume of this thing. The 1/8. I hate 1/8. Okay, I'm just going to do it. The volume, pi r squared delta x, right? This is a disk. We've done disks before. So this is going to be pi. I am not happy. So don't think that I'm thrilled about the situation. I am not. I'm just trying to think how I can make it better. There's no making this better. I mean, we could factor out a 1/8. Yeah, it's just going to be ugly. Let's just leave it. It's the 1/8 is the problem. I hate the 1/8. Why? Why couldn't they have made this 4 up here? Wouldn't that have been better? Okay, but anyway. Yeah, that's what I mean by getting rid of the 1/8. But we can't just get rid of it. It has to go somewhere. So it'll be, okay, let's do what Eli's suggesting. Since one of you came up with it, I feel better about it. So in other words, we're going to do this. Pi times, let's pull out 1/8. Give me a sec here. 1/8 times 24 plus 3x squared. I don't know if this is exactly what you were referring to, Eli, but this is what I was thinking. So this 1/8 times 24 is 3. 1/8 times 3x is 3/8x. So far, everything's true, right? Everything is true. And now I pull that 1/8 out, but notice it's got to be squared. So that becomes pi over 64, because 8 squared is 64, right? Times 24 plus 3x. I guess for that matter, I could have factored out a 3, couldn't I? Let's not. Okay. Whichever you're more comfortable with. The problem is that 8th. The 8 is terrible. I hate the 8. But one of those. Pick one. I'm going to use the bottom one because of Eli. Blame him. But yeah, as long as you have something for the volume. That's my volume. Now we have to get the force. The force in this case is going to be the volume times the density of water. And so in this case, because these are imperial units, aren't they? Yeah, feet. We're going to use 62.5 pounds per cubic foot. Isn't that what they said? You guys have that somewhere? I want to make sure that I'm remembering correctly. Yeah, 62.5. You would think I could remember numbers like that, but okay, so that's the force because pounds are force. So let's do this. It just gets even worse, doesn't it? So the force is 62.5 over 64 times pi times 24 plus 3x squared delta x. We're so close though. So if we can get over, it just, I know it gets worse before it gets better, but we're almost there. Okay, last bit. We need to do work is force times distance. And so how far are we going to drag this particular slice? So I'm going to go back to this picture. So this slice is x units from the bottom of the tank. And so it has to go up 8 minus x units. So for example, if this is the slice that is 2 feet from the bottom, I'm going to have to raise it 6 feet. If this was 4 feet from the bottom, it has to go up an additional 4 feet. But you get the relationship, right? So that's the distance. The distance is 8 minus x. And here's where things get the ugliest, I feel. And so 64 pi times 24 plus 3x squared times 8 minus x is the distance. I'm going to move the delta x to the end. And now I can draw this. This is, I'm going to put 62.5 pi over 64 out here. 24 plus 3x squared, 8 minus x dx. And I'm going to integrate from 0 to 8 because the very lowest that I'm going to have x is the very bottom of the tank is 0, and up at the top of the tank is 8x. And we are pumping this out of this pipe that's at the top of the tank. So that's why I'm only going to go up to the top of the tank, not above the top like that other problem. Anyway, that's the setup. Haven't done the integral yet, but you could, and this is where, you know, it's ugly. You have to square a binomial. Then you'll have a trinomial. You'll have to multiply that trinomial times this binomial. After expanding completely, then you can do your integral, which isn't a bad one. It's a simple cubic. So you're just dealing with a polynomial. So that shouldn't be hard. And then this, as ugly as it is, whatever, it's there. Just leave it there. All right, so the stuff I am most concerned with is all of this setup, all of the work that we did. Is that stuff at least makes sense, even if it's still confusing, difficult, hard. Maybe you're angry. It's okay to be angry. Daniel, what do you think?
Why do we not use integrals for the volumes? Well, we may calculate it up there.
Like, you know, the volume of the actual tank?
Yeah, just like how we did this.
Hmm?
Like, why do we not?
Yeah, so the reason that we aren't just going to straightforward just do the volume of the tank is that the tank, we're not taking the entire tank and moving like if we were to take that entire tank, sorry, this is going to be the tank. If we're going to take that entire tank and move it sort of in the exact shape it is up, then we could just do that. We'd say, okay, what's the volume of this? And then we're going to take that entire tank. In other words, like the bottom of the tank moves up to here, the top of the tank moves in the same amount. The problem is that each bit of this tank is going to move a different distance. So it's a variable. So I guess that the variable here is the distance that you're moving the water. Like this part, the water that's at the top of the tank, it moves, there's no work to be done. Whereas the stuff at the bottom of the tank, we have to do a lot of work to move it all the way up here, 8 feet. So like the stuff at the top, it's like, oh, we got to get this over the edge. There it is. No work done. Stuff at the bottom, oh, okay, now I move it over. So yeah, so it's because of that we can't just compute the volume and then say, okay, we're going to move this whole tank 8 feet upward. Not the case. We do a different amount for each slice. Whew. Anything else? Other things that are bothering you? Wow, we didn't get this far. Here, let me do this. Just give you this so you have something to take with you. This is quiz 7. It's super easy compared with what we just did. So why don't I just let you take this with you, bring it back on Monday, and you can give it back to me. You can do it with a friend if you want to, and enjoy. Otherwise, hope you have a wonderful weekend, restful time, catching up with whatever you need to. So here's a few. There's probably too many. Here's a few. I think there's just enough. Yeah, you can pass when you get it over there. Just send it back, Caleb. There's 2. Enjoy. Here, you can have all of those. Hang on to it. I'll deal with it on Monday. Yeah, I'll hang on to the homework. I'll deal with it Monday. Did you not get one? They didn't hand one back to you? Well, I thought that they would. People, they don't like you apparently. All right. Well, here we are. Looks like there's people waiting for me outside. I'm going to stop the recording. So if you want to come talk.